So basically, I belong to an organization called AVIXA. I'm not sure if you have heard about it or know about it, but that's used to be called as INFOCOMM International until 2017. So this is an AV association of everyone who's into AV industry. So manufacturers, dealers, distributors, system integrators, consultants. So being an association, everything that is being done by the organization is by members. So we have manufacturer members, distributors, dealers, a lot of members worldwide. It's a global organization, headquartered in US, in Virginia. It's close to Washington, but has presence in South America, North America, Europe, Middle East, Africa, APAC, which includes Oceania, Southeast Asia, Asia, Far East Asia, India, and the GCC as well. So I am the country manager for India and the GCC, and I take care of membership development and member development and some strategic initiatives that we do. So what does AVIXA does? So primarily being an association, we are run by the board members who belong to various companies that are part of the AVIXA membership. And we do primarily four things. The first one being provide a platform, a physical platform until recently to people, for the people in the region to meet, to learn, to understand, to see things, provide opportunity to the manufacturers and system integrators to have their booths and do exhibitions. So we have InfoComm US, which happens in the month of June, Orlando and Las Vegas every alternate years. We have integrated systems, which is in Europe, which happens in the month of February this year in Barcelona, which is a co-hosted event with an organization called CDA, which is into home AV needs. We more are a professional AV association. We have INFOCOMM India, which happens in September, but 2023 we plan to have it in the month of October. We have INFOCOMM Southeast Asia in Bangkok, which is going to be called InfoComm Asia from 2023 onwards in another venue next year in the month of May. So it's another 8 months and we are going to have another episode of InfoComm Southeast Asia. And we have Integrate in Australia, which happens in the month of August, and InfoComm China, which happens in Beijing. This year it's going to happen in the month of December, but normally it happens in July. So other than providing physical platform, we also provide a digital platform called Exchange. So it's spelled as XCHANGE, Exchange. So there are some notepads available. You can find us code to access the Exchange, which is basically a kind of platform connecting everyone in the AV industry. So whether you are a provider or an end user or a solution seeker or just anyone who is interested in audio visuals can look into that platform. You don't necessarily need to log in, but you can look at what's happening in AV world around the world in various verticals, in conference collaboration, learning spaces, in conference and events, for example, or any other thing. Any information, any projects that you do, you can post as an individual. So it's like LinkedIn, but for targeted AV people who are interested in AV, not necessarily AV people. It's free for login. It's an open platform. You can look into things that's happening there as well. In case you need more details on that, you can just visit booth H31. We have a small space where we give more details about it. The second aspect that we do is called education and training resources. So AVIXA has a lot of education and training resources. We used to do a lot of hands-on trainings, on-site trainings, virtual trainings, and we have a lot of content for self-paced trainings as well. These trainings are available mostly on membership basis. So we run a membership for individuals, for companies. Then you are able to access the various trainings that are available. And we also run certification. So we are the only body worldwide running a certified technology specialist certification for the AV industry. So I am certified technology specialist in design and installation as well, which I did in 2016. So about 6-7 years now from now. Now, the advantage of certification is you are certified anywhere in the world, people recognize. So if I'm certified, I have never worked in Europe, I have never worked in Southeast Asia, I have never worked in Australia, but by virtue of my certification, I have been able to do trainings, I have been able to do speaking opportunities, because it's one of the things that brings a benchmark that you are a person who will know things for sure. So that's what certification provides. We publish standards for the audiovisual industry. So standards are process standards, management standards, and systems performance and verification standards. So how do you know this image that is being displayed is sufficient for the audience within the space? How is the sound system that is being delivered in the room sufficient and desired and acceptable to be uh, by the end users? So we publish standards. How do you need to consider lighting for a boardroom space or a small collaboration space? Because lighting impacts AV, especially these days when you need to have a virtual meeting, so you need to have video and audio being transmitted as well. And last but not the least, we also have a published lot of market intelligence. So market intelligence in terms of business, in terms of opportunities worldwide, geographically, country-wise. So we publish those data for businesses to look into. And we have also published recently the salary details of level of salaries based on your experience, qualification, certification, region, what to expect for you people to be able to negotiate better salaries and better their career as well. And some of them are available for members, for non-members, and on chargeable basis. I think the salary structure is available for about $99 for a 3-month view, which is a dashboard. It's not a PDF document. It's a dashboard, live document getting updated. For $99, you could look at where you are, and then when, if in case you are negotiating, I would always say that you go and have a look where you stand and then negotiate with your prospective employers. So that's being said, that is being done. Okay, so uh, I have been in this AV industry for last 27 years. I started my career in 95 as a trainee engineer with a company called Philips. It was the projects division of Philips, which used to do audio projects. So communication, audio communication, sound systems, public address systems, airports, transportation, convention centers, conference centers, boardrooms, institutions, and a multiple variety of such applications. So I have had the fortune of learning acoustics. We used to call it electroacoustics as well when you try to combine it with audio equipment and electronics equipment. Uh, but by virtue of being in AV industry for 27 years, I've been working in different parts. So I've been working as a system integrator, as a consultant, in installations. I have had experience of live events examples as well. So well versed with almost all formats of the end use of audio or sound. So today's topic, we are just going through what we call as fundamentals of acoustics in terms of predominantly fixed installations and spaces where there is AV needs that are being met, and what and how to consider factors that influence the AV requirement as such. So just to go back a bit to my first slide where I mentioned AVIXA, AVIXA. So the organization's full form is Audio Visual Integrated Experience Association. So it's not just about audio and visual, but the experience that end users get out of what we do is eventually the most important thing. And eventually we named the association as AVIXA as well. And the experience is something that acoustics of a space affects the end users. And there is a typical uh, understanding of people that acoustics is nothing but wall panels or treatment that you need to give to a space to get good quality sound that you hear. Uh, a lot of places people first have to look at, before looking at the needs analysis, do they really require a sound system? Now, any space that you go, the first consideration you have to look at is whether you really need a sound system before you start looking at what you need to give as a sound system. So, a typical example I would say is a small space where you are collaborating and there is no need for transmission of audio from one location to another. That means the communication is going to be within that space. And if people are able to hear very clearly the way we talk in the normal talking sense, absolutely there is no sound system required. But sometimes you might require a sound system even in such smaller spaces. If you are collaboration, you need audio to transmit or you need to play back pre-recorded audio from a laptop within space, so we might need to do that. So if you can't hear something in the adequate level without amplification, then we probably think of equipment that we might need to use. There is a common terms of lack of understanding of terminologies. So people talk about sound system, people talk about audio system. So what's the difference? What's difference between sound and audio? Anyone wants to share? What's sound? What's audio? Is it the same? Is it different? What's the difference between sound and audio? I would say it's different. Yes. So what's the difference? Sound you can hear, audio you can't hear. Sound you can hear, audio you can hear clearly. Anyone? Okay. So being an engineer, it's easy for me. So sound is the physical form what you hear in your senses. Audio is the physical form converted into electrical signals. When I mean electrical signals, it's not 230 volts, 100 volts. We know it as electronic signals because it's in few millivolts. So a microphone converts my sound from my voice, vocal cords, captures it, converts it into electrical energy, transmits it onto the cable for processing, for amplifying, and pushing it back to the loudspeakers at the adequate level for it to convert back into from audio to sound again. So sound is what output and the input. So when I'm speaking here, it's the input. What you are hearing from there is the output, and everything else within the equipment is electrical signal which you can see. So audio you can see in an instrument, but sound is what we hear. So, and acoustics basically affects both sound and audio. So it's important to understand this aspect, and you cannot control the sound and the audio part by themselves to play around without considering the acoustics. So acoustics is the environment. Because sound is external, sound is what we receive and perceive, it's in the environment. It's important for us to look at acoustics as one of the important aspects. So when we look at it, so the basic objective of this course is to get you acquainted with what are the considerations, why acoustics is important, why it is important for us to know certain things, why are we doing certain things in a certain way, and basically help us in ensuring that eventually people who are using the AV within a space are able to experience it for the need that they desire it, and how and why they are going to use those sound systems as well. So just remove your thoughts that acoustics is nothing but wall paneling, material, flooring, ceiling. Yes, they are part of that acoustics, but it's just one aspect of acoustics, and there are many more aspects which are important when we are talking from the point of view of experience. So the intent of this 2-hour presentation is not to make every one of you an expert acoustician. Even I am not an expert acoustician. I have a lot to learn. I am still learning a lot as far as acoustics is concerned. But basically, this intent of this 2-hour session is that you should be able to recognize the factors that can enhance the sound experience or even the audio experience of people who are in a space, and or even challenge it if when someone says something wrong, and then you can at least point out that that's not what it is and you could change it. So let's look at the definition of acoustics. So it's being defined as the science and technology of sound in all aspects. So basically it covers the production of sound from the source, the propagation of sound within the space. So now propagation of sound within the system is audio, but within the space is sound. So the propagation within the space, the control of sound within the space, the control of sound within a space can happen in the space, or it can also happen in the audio chain. You can control the sound in the audio chain as well to a limited way, and but propagation is only in the physical space. With materials as well as with electronics, that is where the term electroacoustics came in, and then reception to the audience, and eventually how it is affecting the person who is hearing. So let's look at into each of these. So the production is how the sound energy is generated. So what's the source? Typical source of sound that we are dealing with is speech, human speech. But being in AV industry, a lot of us have also to deal with the pre-recorded information, not just speech, but music. Not just music, different kinds of music, different types of music, different types of instruments, having a wide variety or range of it based upon what the end use is. So it's important that if you are able to give an understanding to the source of the sound and then plan your design, that's the first aspect we have to always look at. The best place to fix a problem typically starts with the source. So that's one of the aspects that we always have to look at. The propagation of sound basically looks at the path of the sound, and sound basically is a wave which has energy in it, and sound to audio is nothing but transformation of energy, the physical form of energy into electrical form of energy and back into physical form of energy. So it's a transformation of energy. So when we talk about propagation of sound, we always think of propagation of sound in the air. Right now what is coming from me to you or from loudspeaker to you, basically as if it's coming from me to you. But you also have to remember that sound doesn't necessarily travel through air. Sound can also travel through materials. It can travel through walls. It can travel through ceilings. It can travel through doors. So when we are talking about AV and experience, we also need to consider not just the sound that is being traveled within the space on air as a propagation medium, but also all the physical elements that are there which could transmit the sound and bring it over from one place to another as well. Only vacuum sound cannot travel. Every other space it can travel except for vacuum. So that means it needs something for it to travel, some medium for it to travel, which need not necessarily be air. The control of sound basically means regulating sound energy, generation and subsequent propagation. So generation is how loud I am speaking. So I can control my sound. I can talk softly. I can talk loudly. So that's one point. The second point is I can control the sound by capturing it using an equipment. I can cut it. I can amplify it. So that's another aspect I can do. I can control the sound in making sure that I send sound only to one specific direction and I don't do it in locations where it is not desired. That's another method of control and propagating the sound and how we can control it. The fourth aspect is interaction. Interaction of sound, how the environmental materials that are there, the space is going to affect the sound. The space could be an open. So if it is open, sound is going to travel to all the directions. But if there are objects, sound is going to be, there has to be some sort of interaction between those objects and the sound waves in the physical space, which will impact how the sound is being propagated within a space. You can hear a noise there now. The last is the reception. Reception in our ears and its effect on the person who is hearing. So how our brain is able to process the sound waves received by our ear, converted into electrical signals in a way through our nerves, transmitting it to the brain to convey it into a actionable item as to what is being heard, understanding it or not understanding it. So all those aspects to it. So how do we enhance the end user's reception of sound is the most important focus when we talk about acoustics from an audio perspective. There are many other aspects of acoustics from many other aspects of noise control and other things, but how a human ear experiences sound and is being able to understand it is the most important element. And if you look at the world, anything that is being designed, world of design, we talk about human-centric design. And audiovisual has always been human-centric design because the audiovisual is used for communication purposes. So whether you hear or whether you see. And human-centricity is most important factor. And that is where the need for sound system or audio system has to be established and ensured that it meets the desired use of the humans who are going to use it. So that's the primary criteria that we look at from as far as AV system design or audio system or sound system design is concerned. So when you look at it, so the first thing that you have to consider is how critical is the application. For what purpose is the sound system being used? And then start planning around it when you talk about human-centric design. You all might have looked at the component of sound system are same. So it's microphones and loudspeakers that you see, and then a lot of other electronic devices that you don't see, and then cable, wireless, all those aspects for transmission of audio. Now, if you look at typical applications, so say for example, I am considering a sound system for a learning space, a school, a classroom. Now what's the end user's requirement there? So who are the end users in a classroom? There are two types of end users in a classroom. One is the students who are learning, and the other is a person, teacher, who is teaching. So both of them are end users. So for a teacher, the sound system that you design has to be comfortable for him to be able to speak the way he wants to speak. So, okay, I am provided here with a laptop and a microphone, I'm standing. Normally I would want to walk the talk rather. So I would need a different kind of requirement. I'm not forced into doing anything. Okay, so I can see some wireless microphones lying around here. Now, I want my hands to be free. I don't want to be tied up holding my hand for hours together. Fortunately, my session is 2 hour session. Okay, 2 hours person can manage. Just imagine a teacher, professor taking a class for 8 hours, 6 hours, back to back. So how much of stress or strain he's going to have holding those things. So end users, how they have to use is the first criteria we always use. From the student's point of view, same thing. Students have to sit and not just hear but listen and understand what is being spoken for 8 hours a day, for 20 days a week, 200 days a year, day on day. And that is where the stress and strain of not being able to understand and not the proper system design that is not done right will affect the end users. Similar thing, just look at an airport. So airport also has a sound system. Airport also has a microphone or an announcement. Airport also has a loudspeaker system delivering the sound. Is it the same? Do you need to look at the same design principles? Yes, the primary goal is that they should be able to listen and hear. But the difference is, in an airport, you have to hear and then decide whether you want to continue listening to that sound based upon what is being spoken. In a classroom, that's not the case. You are there in the classroom because of your interest in that subject. So you want to hear and listen and comprehend the whole 2 hours or whole 8 hours. And our brain responds differently to the different aspects. So say in an airport, your announcement has to be made, and say you are flying Thai Airways 291 from Bangkok, say to New York. So now your brain is tuned. You know that you are flying Thai Airways. So as soon as you enter an airport and you start listening to an announcement being made, the first thing that your brain looks at is does the announcement contain Thai Airways? And then it looks at, does it say 291, the flight number? And then it looks at what is being mentioned. And it's 10 seconds, 15 seconds are the maximum announcement durations. Your brain has to work hard only for those, but it's trained to listen to certain things that you want to hear. So you are not much trained, so you can compromise on certain levels of designs. And so the idea was that it's human-centric design. Eventually it's related to acoustics as well. And that is the reason why you find different kind of acoustic treatments in an airport, to a classroom, to a convention center. So depending upon spaces, you need to consider that it's not one thing that fits all. It's unique for different requirements of the spaces that you plan. So, of course, I need to know what is the need of the end users and the criticality of the sound system. Similarly, for example, if a sound system is being designed for, say, evacuation, emergency evacuation, so it must be ensured that people are able to hear and understand in case of emergencies. So, other than the functionality, it's important that you need to know acoustics as well, because that affects how the sound is heard, how the sound is understood, how a human brain reacts to the sound that is being conveyed in a space. So let's look at the propagation of sound. So if I ask anyone, what's the unit of sound? What's the unit in which sound is measured? What's the answer? So instantaneously, everyone would say dB. Decibels. dB stands for decibels. Okay, so is there any electronics engineer here who has worked in wireless microphones, wireless receivers? Even your mobile phones, the radio frequency is shown in dB. RF power is measured in dB. If you go through a data sheet of a microphone, the sensitivity of a microphone, which is supposed to be in voltage, is shown as dB. RF power, which has to be power, everyone knows unit is watt, but RF power in an antenna is shown in dB. So look out, it's just not dB. Sound pressure level, the unit is not dB. It is represented with as dB SPL. dB sound pressure level. A voltage can be represented in decibels as dB V or dBu, small u, small v, capital V variations. So decibels is not a unit. It's just a method of comparing something with a reference. And that reference is something that you need to know. If I'm saying dB capital V, the reference is 1 volt. If I'm saying dB with U, the reference is 775 millivolts. If I say dB MW milliwatt, the reference is to milliwatts, 1 watt or milliwatts. So the reference is important. So decibels just tells you how much is your level as compared to reference level. Is it higher, plus? If it is lower, it is minus. So what's the unit of sound? Simple. Sound is an air pressure. So what's the unit of pressure? Yeah, simple. Pressure, you have measuring pressure is pascals. So the unit of sound, if you really ask, should be pascals. What is unit of audio? Audio signal can be measured in voltage, can be measured in current, can be measured in power. That's why you have that U, V and milliwatt of that electrical signal. Anyway, so sound is produced by vibration of particles in the medium. The medium could be air. Right now the air has a lot of particles which we are not able to see. But there are particles which are moving. In a vacuum, there are no particles, so sound doesn't get a medium to travel. In a wood, wood is a particle. However thick or thin it may be, sound will travel. Concrete is a particle, sound will travel. Carpet is a particle, sound will travel. So it's a medium for sound to travel. Now, vibration basically creates disturbance in the medium, and how much of disturbance is created, at what frequency it is created, basically decides the tonality or what we hear and how we hear things. But it's the vibration. So we can easily relate to the vibrations to a vibration of a string. If you pull a string, it's just vibrating and you could see it. If you drop a water in a wave, drop a stone in water, you can see the waves. So it's anything that vibrates creates what we call as wave. Now, wave is shown in a simple diagrammatic representation of a single wave. A wave is never a single, it's a complex of many waves interacting with each other. But for simplicity, for understanding the concept, it's important that you look at a wave, and sound wave, every wave will have few components to it. So what are the components to it? The first thing is what is called as wavelength. So wavelength is shown as lambda, that's a Greek letter, and one wavelength is for the sound wave to travel, start from 0 to go to its peak in one direction, come back and go to its peak in another direction and come back to the 0. So one whole cycle is basically called as wavelength. So the same concept is used for electrical signals also in terms of what is wavelength, what is frequency, but this is how even the physical sound looks, is like. So the other aspect we need to know, so the wavelength can be small, the wavelength can be large. And wavelength, the reciprocal of wavelength is what we call as frequency. So frequency and wavelength are reciprocal of each other. The second aspect that we need to know is the level of sound, the velocity of sound, intensity of sound. So let's look at wavelength. So if you look at a sound, we consider, now when we say sound is traveling in a medium, so for simplicity, let's assume that the medium is air, normal air that we are there, although based upon what temperature, what humidity, there might be small variations, but let's say that it's air at the moment. It's about 340 meters per second would be the speed of sound in air. So sound can travel from source to destination at a speed of 344 meters within a second. So that's look at it. And let's look at, so wavelength and frequency is something we look at. Again, when we talk about sound, we talk about frequencies, because the range of audible sound is from 20 hertz to 20 kilohertz, although most of us will not be able to hear 20 hertz or 20 kilohertz. But that's the range for the audio frequency, audio signals. So any audio design makes use of that, and then you go between them based upon your requirements. So 20 hertz to 20 kilohertz would be that. If you look at 1 kilohertz signal, 1000 hertz signal, the wavelength of that sound would be almost 1.1 feet, approximately 1 feet. So if you look at this 1 feet, so wavelength of a 1 kilohertz tone is almost 1 feet. That's the wavelength when it's traveling. So when you look at the sound at higher frequencies, the wavelength is very, very low. At lower frequencies, the wavelength is higher. And it's very simple relation. It's a reciprocal relation. But if you see the size of the wavelength wave, 21 millimeter is a wavelength at 16 kilohertz. Is 16? Yeah, 16 kilohertz. And at 500 hertz, it's about almost 0.7 meters is the wave length of the single wave. So the idea behind this is, it's important to understand that even when we say 20 hertz to 20 kilohertz, the sound behaves differently at 500 hertz. Between 500 hertz and 1 kilohertz, it behaves differently. Between 1 kilohertz and 2 kilohertz, it behaves differently. So now, there is one small pattern you must have noted here. If you have noted here, what's the pattern? Anyone has noticed the pattern here? So 500 to 1, what's the difference? Double. 1 to 2 double, 2 to 4 double, 4 to 8 double, 8 to 16 double. Yeah, distance will be half, the wavelength will be half. So it's doubling. So now what we say is, we create a concept of octave. So basically every doubling of frequencies, the response of how sound travels in a medium is going to be different. So how sound travels between 500 and 1 kilohertz is going to be totally different between 1 kilohertz and 2 kilohertz, between 2 kilohertz. And this is something similar to logarithm, log base 2. So sound is logarithmic in nature, and human response of sound is also logarithmic in nature. So although between 500 and 1 kilohertz, it's only 500 hertz of difference, and between 1 kilohertz and 2 kilohertz, there's almost 1000 difference, but those 1000 frequencies behave in a similar way amongst each other as compared to those within this. And this is one aspect which is critical for us to understand, and that's why this is there, because, And this can be seen very simple, very easily here. So 21 millimeter, 2 centimeter is the wavelength of a 16 kilohertz, but this much is the wavelength. So obviously, if you look at any material based upon size, how this one wavelength of this much and how wavelength of this much going together will behave is going to be different. So that's something you have to understand. And of course, the second part is the intensity, the vertical. So how loud is the sound? And loudness is what we look at when we are talking about sound pressure level, when we are talking about audio power. So it's the intensity of the sound that you control. Okay, so let's understand that the sound transmission propagation has to be considered in kind of a logarithmic scale. So the human perception is also worked that way. So every time you double the sound, that is when human will perceive that as a difference in the sound levels. And anything between them, it is not going to matter. So for example, if your sound pressure level that you are hearing is say 70 decibels, I double the sound, and using the logarithmic calculation, 70 decibels will become 76 decibels. 6 decibels change is what we will be able to hear as change. So anything between that, your ears will not be able to perceive that much. And that too a trained ear. So even 10 decibels, a lot of people will not be able to perceive difference of sound between 10 decibels. So it's important for us to understand this aspect, that it is logarithmic in nature and it has to do with the wavelength, the way it behaves and way our human ear behaves as well. I'm not getting into the mathematics. So now unfortunately, acoustics is not just something we talk about materials alone. You have to understand physics, so frequencies, wavelengths. You have to understand mathematics, logarithm, all of these aspects. But it's important that without considering those things, let's look at how we plan out for the sound system in a place. Now, if you look at, so we talked about decibels, that we can relate, or we can say in a way we can measure the sound using decibels. So how do we do that? So we say sound pressure level is 60 decibels, 80 decibels. So basically that means the 0 decibel level, which is what is called as threshold of human hearing, is 0 dB SPL, is what we say as 0.0002 pascals. And if you use logarithmic scale, every 20 dB raise is going to be 10 times. So 10 log of something by something. So every time you multiply this by 10 decibels, you are going to get a plus 20 decibels. So 0.0002 decibels, which is pascals, which is 0 decibels, silence, absolute silence. Although it is called threshold of hearing, no normal human ear will see that as a absolute silence. 20 decibels, which means 10 times this. That means the dot shifts to 0.002 pascals. 10 times this, 20 decibels, silence. No difference. So 0 dB for us is same as 20 decibels. I move this 0 to 0.02 pascals, 100 times. 40 decibels is 100 times. 40 decibels is supposed to be a good treated space which is noiseless. So probably the noise level here at the time, I don't know, I'm not an expert, Uh, it might be around 45 decibels when it's silent, but there are some leakages happening I could hear, so probably it will be giving you 45 to 50 decibels. So 20 silence, 0 silence, 20 silence, 40 silence, 60 is normal conversation at a very low voice that we might have, say in a class, not in a classroom. In a classroom the levels are much higher. Normal conversation, as if when we are standing close to each other, seating next to each other, and if we are conversing, we will be conversing at around 60 decibels. Then 80 decibels is probably more than what you are hearing now. So you might be hearing about 70 decibels when I'm speaking, although it is amplified. 80 decibels is loud sound. So most of our hearing takes place between 60 decibels and 80 decibels. And 100 decibels, rock concert, 120 decibels, threshold of pain. So now your ear starts hurting. So most of the energy that we, sound pressure level that we use is typically between 60 and 90 decibels for the AV use. Okay, so now when we talk about sound, when sound is generated, say I created this sound or something falling, so there are waves that are traveling from here to there. If you plot the waves in timeline, so what happens? So as soon as the sound is created, from the time the sound is created, within few milliseconds, you will have the direct sound. 344 meters per second sound takes to travel, and you are able to hear the direct sound. But it doesn't stop there. The sound is continuing. And it has not come in the single direction. It has gone omnidirectional. It has hit the roof, it has hit the ceiling, it has hit the chair, it has hit your body, it has hit this flower. It's hit everywhere. So what we say is, after the direct sound, there are some reflections of sound that comes. They are called as early reflections and late reflections. Now, for human experience, it's not just the direct sound that matters. You need the direct sound along with reflections for you to experience a good sound. And which reflections and how much of it is again something that depends upon what the system is being used for. So typically for speech, reflections up to about 35 milliseconds in time is good to give the quality of speech for people to be able to understand properly. And so we would want direct sound with some of the reflections within the 35 millisecond range. For music and instruments and a lot of other stuff, we might want some late reflections as well to give the tonality, to give the quality of the sound that is being generated. So you might receive some more reflections. And every reflection that comes after that, your ear starts to receive as multiple sounds. And so you could call it echo, or late reverberations. So it's like hearing multiple times of what you are hearing. And very late ones will be echo. You are hearing two sounds. Now again, if you look at the level, so now how much this has to be from this original sound. So the reflected sound are not same as direct sound, because reflections have caused loss of sound because of the distance it has traveled, because of things in the medium, because of some sort of absorptions that happens. So those are the phenomena that we are going to see as well. And so the levels are a bit lower than the direct sound, but put together they create what we are desiring to hear. And then reverberation is something that you have to see, depends upon the space, depends upon interaction of the sound waves with the material in the space, the size of the space, size meaning the volume of the space. So volume means length, breadth, as well as the height. So it's a three-dimensional volume space considerations that decide. Limited amount of reverberation is something that is also desired depending upon what the task is. So this is just a depiction of how a sound wave hits, what's the early reflections, what the late reflections, reverberation, and then anything beyond the reverberation would form what we call as the echo or undesired sounds. In a small spaces, it's typically the timelines, because the space is so small, almost the reflections will be coming at the same time, so the chances of reverberations are much lesser. So the lesser the volume, lesser the reverberations. As the size starts increasing, the volume start increasing, you are prone to more reverberations. So that's one aspect that we need to look at as far as the sound is concerned. Now, there is one dotted line that you see here, which is on the level scale. So that's what is being mentioned here as the ambient noise level. Noise level when nothing is being spoken, no airwaves, and no airwaves created for people to hear or listen to, but what is available in a space because of various reasons. So now, again, this is something which will depend upon the space, and acoustics is very important to consider because that is not just used to improve this listening, but acoustics is also used to control the ambient noise. The lower the ambient noise, the better is going to be the performance of sound, because better is going to be the human intelligibility, because it's the noise that creates the disturbance, that increases the working of the brain to be able to listen to and hear things. So acoustics, we not only do these things, but we also look at how do we control the noise. So when you look at, and there are ways to measure it, and that measure the way we measure the performance of a space, of how space functions for acoustics, is by using what we call as impulsive response. So impulsive response is sending a burst of sound in a space created. These days it is created by laptops, it could be created by instruments. The type of wave is also important, so it could be a sweep wave, that means some frequencies at different, so starting from say 20 Hertz to 40, so again I said doubling, so 20, 40, 80, 120, 240, so you continue 480, but rather than using 480, you use 125, 250, 500, 1000, 2000, 4000, 8000, 16,000. Because it's easy for humans to remember those numbers than anything else. So again, it depends upon what you create. It doesn't matter if it is 120 Hertz or 150 Hertz. You know that between 0 and 500, it's almost going to be very, very similar how they work. So sound is created in a source, and then the response is measured using a microphone, omnidirectional microphone. So you create a source, you measure the response, and then the mathematical tool helps you to analyze what's happening. How much is the direct sound pressure level, at what time it is arriving, how many reflections are arriving, at what level they are arriving, for what duration they are arriving, and it can be used to calculate eventually all the factors that are needed for calculation. Most of the time it's going to be reverberation time, but it could also be trying to calculate even parameters like speech transmission index, which basically gives how intelligible sound is. So impulse response is one of the tools. There are many tools available for you to create these, analyze these, and give you in understandable format what's happening in the space. Now, we know that sound, when it is generated, it goes in all the directions. And here comes a law called as law of conservation of energy, which basically states that energy can neither be created nor destroyed by any process. It can only be converted from one form to the other. So here it's very simple that the sound energy that is being generated cannot be lost. Something is, vibrations are generating those sound waves which are creating those sound which is getting impacted in the environment, but it is going to be converted into some other form of energy. Electrical energy in humans again, so we have the ways of converting physical waves into neurons, which basically convert it into electrical energy for our brain to decipher. Similarly, so the way that sound energy interacts with the environment, there would be, the first thing that happens is reflection. So a part of sound waves are reflected back to the same space. How much level, what frequencies, those depend on that material. And because frequencies again, wavelength, size of wave different, so size of material matters, type of material matters, shape of material matters, because shape decides where it has to be reflected. So the first thing that we use is reflections. And when you say reflections are desired or not, a lot of times it is. If I have this space by virtue of which, you don't forget that there is a microphone, I'm talking, and the space has been designed in such a way that the energy is directly transmitted as well as the reflected energy are created from the walls, so that the whole energy is used within the space. That's creating the space to use for audio and sound transmission without doing any reinforcement using electronics. But that is going to become a very, very difficult task. A lot of things, probably it's easier to do that using an electronic system than to use that. And that's exactly the genesis of sound systems. Although in the past, I think there have been installations where you get to see these phenomena in real life. I think you can relate. So you all know pagodas, right? So you have pagoda in Thailand. I have seen pagoda in India. So I have seen a pagoda which is nothing but a hemispherical stone structure, fully made of stone. Outside they have a lot of other things, but if you go inside, it's just a dome. So there is a dome which is 90 meters away, 90 feet diameter. You stand on one end, I stand on other end. I talk to you in a very normal, soft conversation. You are able to hear very clearly, and vice versa. 90 feet away. As soon as you start shouting, nothing will be heard. So now that's happening naturally. But that cannot be expected to all the spaces that we design for schools, for institutions, for airports, for classrooms. So we can't expect on those aspects to play with the sound system. So we start thinking of what do we do. So obviously we can look at trying to see if we need some reflections that can help the sound system design. So architects look at that. There is absorption of sound in any material. Every material, there will be some sound which will be absorbed. Basically, it's converted into heat energy or some other form of energy. And then there is sound getting transmitted. So transmitted sound is sound being able to pass through the barrier to the other side. Now there is also, because of the wave sizes, depending upon the size of the objects, some other phenomena happening there as well, which we will try to look at. So if you look at the wall, so the space here, so I'm sure sound gets reflected from these walls, sound gets reflected from the floor, sound gets reflected from the ceiling, sound gets transmitted through the walls, sound gets transmitted through the glass, through the door, it gets transmitted here, through the door outside. Sound gets transmitted from outside to inside as well. So it's not just that what I'm talking is going out, but something that's happening outside. Transmission happening from up, transmission happening from floor below. Now, it's important that the way we design, the desired sound, the reflections are advantageous to us or maybe disadvantageous to us, and we have to see how this space is before we plan our actions. Now, when we look at reflections, and let's not look at multiple reflections, let's keep it simple. A direct reflection will occur when the size of the obstruction is relatively large compared to the wavelength. So higher the wavelength, the bigger should be the size for it to reflect it. So now when we saw the wavelengths of say 2 centimeters, 5 centimeters, so even small surfaces would be able to reflect it. But low frequencies, you really need very, very large, big surfaces for it to be able to reflect it in what we call as specular manner. So just for simplicity, it's shown as a single arrow, just for you to understand that the reflections can be made use of in the spaces by using adequately sized materials to take advantage of these. Now obviously, when a reflection happens, say this is the source, direct sound coming to the destination and a reflected sound. So there is going to be a difference in sound coming from these two paths. And again, these reflections could happen with multiple pathways as well. So there will be cancellations, there will be additions of wave, superimposition of wave, a lot of things that also happens. And whenever we show it in simple diagrammatic manner, it's very difficult to understand sound as such, because it has so many various frequencies that this whole diagram will become very complex if we start looking at multiple frequencies. So it's always good to understand from a single frequency point of view, and typically we use 1 kilohertz or 2 kilohertz to depict sound. It's in the center of our hearing response. Now, so you could use an effective reflector in a space to get some amount of desired sound, even if you are designing any spaces as such. Longer wavelengths, that means lower frequencies, say 500 hertz, 200 hertz, because you need huge materials, so they can go beyond the material size, so they can bend over those spaces, they can go over. Depending upon mass, how much of sound is getting transmitted or reflected is also affected by mass of the structure. So that's another aspect that we should look at. Now, again, it could be useful, it could be distractive, but the effort of a typical sound or space design is to make efficient use of the space to get best out of the sound that is being delivered, as well as try to look at human point of view as to avoid multiple reflections, try to get more of direct sound. And when I mean direct sound, it means direct sound plus early reflections. and less of reverberation when you are delivering speech, because reverberation creates problems in intelligibility aspects or understanding aspects of speech. But for music, you would still need some amount of reverberations to give the naturalness of the spaces. If you are building a studio, again, you need as much direct sound for a recordist to get full amount of voice directly, rather than getting reflected sounds and capturing it to give create issues. So that's going to be a different. Small rooms, reflections are so they're hardly at within 10 milliseconds or 20 milliseconds that they are hardly going to matter in a big deal. So small rooms, typically acoustic treatment for the purpose of reflections is not there, but there's whole another thing that comes into play when you're talking about small rooms, which we will talk, which needs to be considered. Large rooms, huge rooms, the reverberations come into play, so you need to have more controlled reflections and absorptions in order to design the space. So reflections have been used in a lot of designs to be useful for you to send the sound in the directions that is required. Typical auditorium seatings would be an example, where you could create reflectors in the ceiling to ensure that you get desired reflected sound. Basically, getting the sound, natural sound, is much more easier for you because you are saving on the equipment power that you need to generate that much of sound pressure level otherwise. Okay, so of course these illustrations are very simple to look at, but it's not going to be as simple because we are showing only the reflections from ceiling. Understand that reflections are going to come from all the spaces, from the side walls, from the floor, from the chair, from people. But it's just for us to look at that this is something that is typically done. Now, when we talk about typical spaces, if you look at that we design AV for, almost 95% or 90% of them will be some sort of rectangular spaces, rectangular or square spaces, for example. So obviously it will have walls on two sides. So there is one particular phenomena that affects because of the parallel walls, and that's basically the flutter echo. So what happens if I stand in the room and create, I can hear flutter echo here. So there are late ones reflections, but you can see that the sound is getting hit and coming back. So these are flutter echoes, which are, so when a sound is created, source is created, you start hearing those as well, and that has to do with the walls. And again, designing what type of absorption you require is going to be a very, very humongous task because of all the various factors that you need to look at. Okay, so very common flutter echoes, we see that, and that has to do with the parallel surfaces. So that's something we always look at. Then you have small rooms. Have a peculiar problem as well. So reverberation is not a problem in a small room, but small room have a peculiar problem, what we call as room modes. And again, that has to do with the physical property of a wave. So if you look at the wave size, say for example, there is a room which is 36 feet long. Okay, now if I look at a frequency, say 32 Hertz, the wavelength of that frequency will be almost 36 feet, almost the same size of the space. So the length of the wave matches the physical size of the space. So what happens when a sound wave is created at that particular frequency? The waves remain there, and it becomes what is called as standing wave. So although a wave is created, because the wavelength is the same as the length of the room space, so it happens that the wave in those particular frequencies remain there. And similarly, there could be some frequencies for this based upon the dimensions of this. So now what happens is, if you look at the wave is something this. So there are spaces where you are going to have too much sound. There are spaces you are going to have no sound. There are going to have spaces again too much sound. And there is absolutely no way you can do anything, because that's how that space is, and that's the size of the wave itself. So room modes are a problem in majority of the small rooms, collaboration spaces that you create, and that has to do with the shape of the space, which is usually rectangular, two walls, and two walls. And if you look at the three-dimensional space, the room modes is also going to happen in all the three. So it has, the waves will be within this, the waves will be within this, and the waves will be within this itself. And the combination of all the three is going to create a still different response to those frequencies. And eventually those frequencies, when you actually go and measure things in those rooms, you, because of room modes which you cannot avoid, you will get those imperfections in the space. And this happens mostly in the low frequency range. So what do you do? So one way is not to have these rectangular spaces. So create some very different shapes of spaces where you avoid. So have ceiling, different walls, different flooring has to be flat anyway. But yeah, so, but then there has been research done wherein there are certain dimensions that can be avoided, or certain dimensions that you can consider in terms of small spaces to avoid room modes. So there are a lot of such researchers who have worked out their own formulas. So now this is basically a ratio of height to width to length of the room. So they have created for certain specific ratios within the specific range that you can still go ahead and create rooms that fall within this range to be able to avoid room modes. Or you don't go for a rectangular space, try to create imperfections in the space, or some change the parallel walls so that you are not able to get those. So the relative proportioning of length to width to height of a room is one way in which you could control the room modes for the application that you possibly would be looking at. Now comes the large rooms. So large rooms have to deal with reverberation, and again it has to do with the natural size. Because of the size of the space, the time traveled by the direct sound with respect to the reflected sound is going to increase, which is going to create multiple late reflections, which is going to create problems with speech intelligibility, which is going to affect the experience of humans to be able to listen to the sound. So large rooms, large halls, auditoriums, gymnasiums, assemblies, legislative assemblies or parliaments, temples, churches, mosques, they are large spaces for congregation of many people. And if you need to create those spaces, then you have to look at acoustics from the point of view of controlling reverberation. So what is reverberation? Now, typically reverberation is shown as RT60, reverberation time 60. Now what is this 60 here? 60 means 60 decibels. So 10 decibels 10 times, sorry, 20 decibels 10 times, 40 decibels 100 times, 60 decibels 1000 times. So time taken for the sound energy to go from maximum to minus 60 dB, 1,000th of its original level, is what is called as reverberation time. Now again, this time is dependent on the volume, the materials, the wavelengths that are getting generated, and how they are within a space. So to control these, it's not just the design requirement of what you think you would consider, but also the space, the size of the space, again the dimensions of the space and the materials used in the space. So the advantage, and our reverberation time is something that can be measured as well with the tools that are available, and what is being done is there are standard reverberation level times allowed that are provided for by on the basis of typical spaces or applications. So for example, again, it depends on volume. So if you see here, as the volume of the space goes up, the reverberation time automatically goes up. So depending upon the application and depending upon the volume of the spaces, so there are some support documentations or research information available for you to plan reverberation time and then plan your design based on what reverberation time can be achieved. So controlling reverberation time is going to be by the interiors, by the material used, by the size of the space, and not by the sound system designer who can create that. Sound system designer can use this information of what RT that I will be getting here to design his sound system to be able to provide the necessary intelligibility. And again, that depends upon the application. So recording studios are very stringent in what RT time they can have depending upon the size. So 10,000 square feet, the level is 0.4, which is very good, no reverberations actually. Anything above 1.2, again, as you go into the musical applications, you can have higher reverberation times acceptability as well. Okay, now making use of the properties of reflections, you can control some amount of reverberation time as well, and that is where the interiors designers plan out the spaces. So it's very similar to the properties that are exhibited say for example in a projection screen. So when you look at a projection screen, your light is hitting and coming straight back, but if there are imperfections here, then it's not going to be clear, so there will be shadows generated. So what happening is that imperfections in the space, in the wall, is going to create multiple reflections called scattered reflections, and you can use these scattered reflections to avoid reflections and control the reverberation time in a space. So this is the way, again, you could create the material or the walls in the space to have these diffused reflections They are typically called as absorbers and diffusers. So because they are made of material that can absorb as well as reflect energy in a diffused manner for you to get advantage of lower reverberation time coming out of it. So this is another requirement. So now again, so do you need diffusers in a small space? Why do you need? So that has to be really justified based upon what those diffusers are for. Are they there for absorption? Are they there for reflections? Are they there for useful reflections? So that's something you have to look at. Now, when I talk about these things, it's very easy to talk because I can say sound is generated. So right now it is generated from here on those ceiling loudspeakers, but it could have been generated using a wall mount loudspeaker at another location. So now when multiple people speak, multiple locations of sound will create a different effect for the same system to provide sound as well. So that's another characteristic. So where is the person who is speaking from? How is the person speaking from here or there going to affect the response? So those are the things that need to be looked at as well. So when we look at these and also consider that, as we said, the size and shape is for the frequencies that you need to control as well, because every frequency will have a different wavelength and that's going to have a different kind of interaction. So the way these are done is by actually analyzing the space, using instruments and seeing what's actually happening there, and then trying to get into the way of trying to control or design the space. And that's exactly where good design will help you in creating a good experience. Now, so these were all reflections being used. So advantages, disadvantages, all things we've had looked at. Sound is also absorbed. And again, absorption depends upon frequencies. So a 2 kilohertz frequency will be absorbed differently by the same material than a 250 hertz, which typically would be reflected most of it. Low frequencies typically are reflected away unless you use huge absorbers to match those wavelengths. And most of the absorbers will have no effectiveness for low frequencies. So less than 250 hertz, absorbers won't play a role at all. They are all there. They will work only for higher frequencies and not for lower frequencies. So if you look at absorbers, there are many different types. So you have porous absorbers, which basically is used for mid to high frequencies. Again, you could look at what frequencies. So most of the times you will find frequencies from 125 hertz to 8 kilohertz or 16 kilohertz being mentioned, because that's where most of the speech frequencies are. 125 hertz to 12.5 kilohertz is the speech. 50 hertz to 20 hertz to 20 kilohertz is the full audio range. Music typically can have lower and higher frequencies around 50 hertz and 18 kilohertz as well. So trying to control absorption of higher frequencies or mid frequencies which affect speech, we could use porous absorbers. So you could find blocks with a specific type of material that will be used to absorb these. Then you could use resonant absorbers because of the size of the resonant frequencies or wavelengths that create those frequencies. They are called resonant absorbers. So they are used for mid to low frequencies, and they can be membrane type, they can be panel type, and they are used to absorb the mid and low frequencies. So analyzing what needs to be controlled is more important before you choose what type of absorbers you use, and you just don't put something just assuming that it's going to do what you are going to use. Then of course the mass of the object, the mass of the material that you are using plays an important role by what we call as a mass law. So when sound travels, some of it is going to be transmitted through the structure, through the material, and the mass helps in trying to absorb certain higher frequencies only. The lower frequencies are not affected. How much ever thick you put the structure, it's going to affect certain higher frequencies only, and it's not going to affect the lower frequencies at all. So that's another thing. So you can control, by controlling the mass of the object, only frequencies within a specific range and not the rest of them as well. So when people plan for these spaces, they look at all these aspects before deciding what to use and why to use. So that's always important for us to remember. Very low frequencies, you cannot stop the transmissions at all. So for example, vibrations happening is nothing but sound, very low frequencies getting transmitted, which cannot be controlled by anything except probably structurally you have to create isolations to work out those. So there is a property called as transmission loss, and then there is a word used called as sound transmission class, STC, which basically is the kind of material and how much of transmission you need to control between two spaces. So for example, if we are talking in this room and there is another room close by, ideally speaking, I should not have transmission between these two rooms. I have to try to control as much as possible. But it is also a design phenomena. There is a rating, what we call as STC rating, which basically gives you what and how you plan the physical demarcation between these two places. So, and this is the necessity of privacy. So it could be privacy, it could be non-interference, where 0 to 20 STC means absolutely no privacy. You have not considered transmission as a criteria between the spaces, but higher transmission class is required between spaces where you have functional requirements of working out those. Having said that, manufacturers of products that are used for absorptions or preventing transmission or controlling transmission, they create products or they design products based upon these considerations, and then they give the values of those. So anything connected using any physical mechanism will be contributing to sound travel. So one way to avoid vibration travel is to isolate those two or decouple those two completely. A lot of places, so for example in hotels, if you see wall panels are the glasses are there, but there will be double glasses, and some of them could be creating a vacuum between those two glasses,